Right now, the ESA Juice probe orbiting between Earth and Jupiter is observing a spectrum anomaly from interstellar comet 3I Atlas at 1420 MHz, the hydrogen line, modulated in 37-second pulses, which contradicts every known mechanism for natural comet outgassing, leaving scientists unsettled. The signal appeared 47 minutes before the comet's closest approach to Venus, transmitted in a data packet labeled Anomaly 7, and within hours the ALMA radio telescope in Chile confirmed reception of an identical pattern with a 2.3-second delay, as though something trailing behind the comet's nucleus is reflecting or retransmitting the emission. This is not how ice sublimates. This is not how plasma behaves in a solar wind. And 1420 MHz is not a frequency the universe chooses at random. It is the fingerprint of neutral hydrogen, the most abundant element in existence. And for precisely that reason, it has been called the universal frequency the channel astronomers agreed decades ago any technological civilization would monitor or use to announce itself. The wavelength is 21 centimeters. It penetrates dust. It crosses voids. And now, on November 3rd, 2025, at 1412 UTC, it is pulsing from the third confirmed interstellar visitor ever observed, a comet on a hyperbolic escape trajectory that will never return. Marcus Landgraf, ESA lead astronomer, offered a poetic metaphor yesterday. Two wanderers meeting in a desert. Today he has gone silent. His team is analyzing noise. Avi Loeb, the Harvard astrophysicist who argued that Oumuamua might have been a light sail or debris from alien technology, is live on X, writing 2 sentences that have already been screenshot and shared 160,000 times. This isn't dust, it's modulation. 47 minutes before periapsis, the moment of closest approach between 3I Atlas and Venus, Juice telemetry dropped for 11 seconds. When it returned, the data stream included spectral measurements that should not exist in nature. Not from a comet, not from ionized gas fluorescing under solar ultraviolet, not from any collision or impact chemistry documented in 70 years of cometary science. The Venus flyby was supposed to be a gravitational handshake, an opportunity to watch solar heating and tidal stress rip volatiles from the nucleus and blast them into space, forming jets visible across millions of kilometers. Scientists predicted brightness spikes. They anticipated water, carbon monoxide, methane, perhaps even organic molecules synthesized in the cold molecular clouds between stars. What they did not anticipate was a carrier wave. Because that is what modulation implies: information encoded onto a signal, the way AM radio encodes voice onto an electromagnetic wave by varying its amplitude, or FM by varying its frequency. The 1420 MHz line detected by Juice does not merely exist. It oscillates, it repeats. Every 37 seconds, the intensity rises and falls in a pattern stable enough that 2 independent instruments, one in orbit, one on Earth, captured the same sequence. Paul Chodas, director of NASA's Center for Near-Earth Object Studies, canceled his scheduled briefing at 15:00 UTC. His office at the Jet Propulsion Laboratory in Pasadena is sealed. No statement has been issued, but 3 sources within CNEOS, speaking on condition of anonymity, confirmed that NASA's Deep Space Network has been retasked to focus every available antenna on the comet's trajectory. One source used the word protocol. Another said, "We're treating this like first contact until we prove it isn't." Stop and consider that. CNEOS exists to track asteroids that might threaten Earth. It calculates orbits. It refines impact probabilities. It does not typically invoke first contact protocols, because those protocols are reserved for SETI, the search for extraterrestrial intelligence. And SETI has spent 6 decades listening to the sky without hearing a whisper that could not be explained by pulsars, quasars, or magnetospheric noise. Until now, every candidate signal has dissolved under scrutiny. The famous WOW signal of 1977, detected at 1420 MHz, was never repeated. Dozens of fast radio bursts turned out to be distant cosmic explosions, not alien beacons. Breakthrough Listen, funded by Yuri Milner and advised by Stephen Hawking before his death, has surveyed millions of stars and found nothing. 3I Atlas is different. It is not a star. It is not stationary. It is moving at 34 kilometers per second relative to the Sun, outbound on a trajectory inclined 47 degrees to the ecliptic plane, and it came from the direction of the constellation Triangulum, approximately 12 light-years away. If you trace the orbit backward and account for proper motion of nearby stars, it will leave the solar system faster than it arrived, accelerated by the Sun's gravity into permanent exile, and it is transmitting something that sounds designed. Comets are dirty snowballs. They are agglomerations of ice and rock and organic grime, leftovers from the formation of planetary systems, and when they fall toward a star, the heat vaporizes their surface layers, releasing gas that glows under ultraviolet light and carries dust into space. The gas expands. The pressure drops, molecules collide less frequently. Emission lines appear in the spectrum, signatures of water, carbon dioxide, cyanogen, sometimes ammonia or methanol. But those lines are broad and messy, shaped by temperature and velocity and the chaos of sublimation. They do not pulse. They do not modulate. They certainly do not repeat on a 37-second clock with the kind of periodicity that implies a rotating source or an intentional broadcast. And yet, Ophelia King, mission leader for JUICE, held an emergency teleconference at 1630 UTC with ESA's Science Directorate and representatives from NASA, the European Southern Observatory, and the International Asteroid Warning Network. According to two participants in that call, King presented preliminary analysis showing that the 1420 MHz signal strength varies by approximately 18% peak to trough, and the modulation envelope is not sinusoidal. It has structure, a shape that resembles a double peak separated by a 4-second dip, then a slow decay. One participant described it as almost like a heartbeat. Another said, "We need to rule out instrumental error. But if this is real, we don't have a natural explanation." JUICE was not designed to hunt for aliens. It was built to study Jupiter's moons, Europa, Ganymede, Callisto, frozen worlds that might harbor subsurface oceans and possibly life. The spacecraft carries a magnetometer to measure magnetic fields, an ice-penetrating radar to probe beneath moon surfaces, and a suite of spectrometers to analyze composition. One of those instruments, the submillimeter wave instrument, can observe wavelengths from 530 to 625 GHz. But the probe also carries a communication system operating in the X-band and K-band. And it is that system, designed simply to phone home, that detected the anomaly. The signal is not coming from JUICE. The signal is coming from the comet, or from something in the comet's vicinity, and JUICE happened to be listening. ALMA, the Atacama Large Millimeter Array in Chile, is different. ALMA is an interferometer composed of 66 radio dishes spread across the high desert at 5,000 meters altitude, and it was purpose-built to observe the universe at millimeter and submillimeter wavelengths. It can resolve the disks around newborn stars. It can image molecules in distant galaxies. And on November 3rd, operating in its 21-centimeter band, it locked onto 3I Atlas and recorded the same 37-second pulse sequence, but delayed by 2.3 seconds relative to the JUICE detection. If a signal originates at the comet and travels to JUICE, it covers the distance at the speed of light, 300,000 kilometers per second. If the same signal travels to Earth and reaches ALMA in Chile, it covers a different distance, and the travel time differs by however far apart the two receivers are along the line of sight. JUICE on November 3rd was approximately 420 million kilometers from Earth, positioned between Mars and Jupiter on its long voyage to the Jovian system. The comet, at Venus flyby, was roughly 150 million kilometers from Earth, hidden behind the Sun from terrestrial observers, but visible to space-based instruments. The geometry means Juice was closer to the comet than ALMA was, so the signal should reach Juice first, and it did, by 2.3 seconds. That matches the light travel time for the extra distance, which means both instruments saw the same event, separated by the time it takes light to cross the gap. That is not an instrumental glitch. That is not interference. That is a real electromagnetic emission, originating in space, propagating outward in all directions like ripples on a pond. But the delay has another implication. If ALMA sees the signal 2.3 seconds after Juice, and if the source is moving and the comet is moving at 34 kilometers per second, then during those 2.3 seconds the source travels about 78 kilometers. That is roughly the size of a small city. And if something near the comet is reflecting or retransmitting the signal, then there is a second source displaced from the nucleus by tens of kilometers, trailing behind like a shadow. And that shadow is coherent enough to reproduce the modulation pattern with high fidelity. Think about what that means. Comet nuclei are typically a few kilometers across. 3I Atlas is estimated from brightness and assumed albedo to be somewhere between 1 and 4 kilometers in diameter, about the size of a mountain. Its coma, the cloud of gas and dust surrounding the nucleus, can swell to hundreds of thousands of kilometers under strong solar heating. But the coma is diffuse, a fog with density dropping exponentially with distance. If something 78 kilometers behind the nucleus is retransmitting a radio signal, it is either an unusually dense clump of material, a fragment that broke off and is coasting along the same trajectory, or it is discrete, an object with enough structural integrity to remain distinct from the coma. Or it is an artifact of the observation, a side lobe in the radio beam, an echo off the ionosphere, a miscalculation of the Doppler shift. Except that multiple teams have now checked the geometry. The JPL Horizons Ephemeris, which provides position and velocity vectors for solar system bodies with extraordinary precision, confirms the comet's location. Radar ranging from Goldstone, part of NASA's Deep Space Network, measured the distance to within a few hundred kilometers. The numbers work. The 2.3-second delay is real, which means the trailing source, whatever it is real. Read between the lines. ESA has not issued a press release. NASA has not scheduled a press conference. The usual communication channels, the ones that announce discoveries of exoplanets, or black hole images, or gravitational wave detections, are silent. Instead, information is leaking through social media and private conversations, a pattern consistent with either extreme caution or active suppression. Elon Musk, CEO of SpaceX and owner of the Starlink satellite constellation, posted on X at 17:04 UTC. Starshield is picking up the same. This isn't noise. Starshield is the military-oriented version of Starlink, a classified satellite network designed for secure communication and surveillance. If Starshield has detected the 1420 MHz signal, then the phenomenon is not restricted to scientific instruments. It is broad enough, strong enough, or persistent enough that a constellation of small satellites in low Earth orbit can see it. That raises the signal's credibility. It also raises its strangeness. Starlink satellites are not radio telescopes. They are communication relays equipped with phased array antennas optimized for X-band and Q-band, frequencies far above 1420 MHz. For Starshield to detect a 21-centimeter signal, either the satellites carry additional sensors not disclosed in public filings, or the signal is so intense that it bleeds into adjacent frequency bands, or Musk is bluffing. But Musk has a history of inserting himself into high-profile science stories, sometimes helpfully, sometimes not. And his companies have contracts with NASA, the Department of Defense, and intelligence agencies. If he says Starshield sees it, someone inside those agencies is probably confirming that claim. Which brings us to the comet itself. 3I Atlas was discovered on January 9, 2025 by the Asteroid Terrestrial Impact Last Alert System in Hawaii, a network of 4 telescopes that scan the sky every night looking for moving objects. The designation 3I means third interstellar, following 1I Oumuamua in 2017 and 2I Borisov in 2019. Oumuamua was bizarre, elongated, tumbling, accelerating slightly as it left the inner solar system in a way that could not be explained by outgassing alone. Loeb proposed it was a light sail, a thin reflective sheet pushed by starlight, either debris from alien technology or an active probe. Most astronomers rejected that idea, favoring exotic but natural explanations like hydrogen icebergs or nitrogen flakes. Borisov, by contrast, was boring. A normal comet, chemically similar to solar system comets, behaving exactly as expected. 3I Atlas split the difference. Its orbit is definitively hyperbolic, with an eccentricity of 1.032, meaning it came from interstellar space and will return there. Its composition, judged from early spectroscopy, includes water, carbon monoxide, and silicate dust, standard comet stuff. But its activity is strange. 4 days ago, on October 30th, the comet passed perihelion at 054 AU from the Sun, closer than the orbit of Venus, and its brightness surged by 20 to 30% within a few hours. Comets often brighten near perihelion because solar heating vaporizes fresh ice, but the surge was sharper and faster than models predicted. Some researchers speculated the nucleus fractured, exposing pristine material. Others suggested a subsurface cavity collapsed, releasing a burst of trapped gas. Now there is a third option. Something on or near the comet activated. The 37-second period is too regular to be random. Natural processes, rotation, precession, oscillation, can produce periodic signals, but they drift. A comet nucleus tumbles chaotically because outgassing creates uneven thrust, like a spinning lawn sprinkler. Pulsars, the rotating neutron stars that sweep radio beams across space like lighthouses, are famously stable, but even they slow down over time as they lose energy. A 37-second period is unusually long for any natural rotator in space. Earth rotates once every 24 hours. The Moon rotates once every 27 days, but tidal locking synchronizes that with its orbit. Asteroids spin in minutes to hours. The only objects with periods of tens of seconds are either very large and slow or very small and deliberately stabilized. If 3I Atlas's nucleus is rotating every 37 seconds, that implies a spin rate of about 1.6 degrees per second. For a 2-kilometer object, that means the surface at the equator moves at roughly 100 meters per second, fast enough to feel significant centrifugal force, but not fast enough to tear the object apart. It is plausible. But if the signal modulation is tied to rotation, then there must be an asymmetry, a bright spot or an emitting region that sweeps past the observer once per rotation, like a pulsar beam. And that asymmetry must be stable, unchanged over the hours between the Juice detection and ALMA confirmation. What could produce that? A jet of gas, fluorescing in ultraviolet light, might brighten and dim as the nucleus rotates and the jet swings in and out of view. But jets emit across a broad spectrum: optical, infrared, ultraviolet, not at a single radio frequency. A magnetic field, interacting with the solar wind, might generate radio emission, but comets do not have strong magnetic fields. Their nuclei are too small and cold to sustain a dynamo. A plasma instability, like those seen in the ionospheres of planets, might oscillate, but 1420 MHz is a very specific frequency, not a broad hiss or crackle. That leaves technology, not necessarily alien technology. Human spacecraft also emit at 1420 MHz, although it is an unusual choice for deep space communication because the frequency is crowded. It sits in the so-called water hole, a protected band that radio astronomers worldwide have agreed to keep quiet for SETI observations. NASA's Deep Space Network typically uses X-band around 8 GHz or K-band around 32 GHz, where antennas can be smaller and data rates higher. But some older spacecraft, particularly those designed for interplanetary missions in the 1970s and 1980s, carried experiments that transmitted at 1420 MHz to test propagation or search for scattered signals. Could 3i Atlas be carrying a defunct probe? The idea is not as absurd as it sounds. We have sent 5 spacecraft on trajectories that will eventually leave the solar system: Pioneer 10 and 11, Voyager 1 and 2, and New Horizons. All 5 are now beyond the orbit of Neptune, coasting into interstellar space, and all 5 will wander the galaxy for millions or billions of years unless they collide with something. If another civilization did the same, if they launched probes to study their stellar neighborhood, or to seed the galaxy with messages, or simply because they could, then some fraction of those probes might still be drifting. A few might, by chance, fall into our solar system, and if one of them passed close to the Sun, solar heating might reactivate dormant electronics, triggering a transmission. That scenario has been called the interstellar probe hypothesis, and it is taken seriously enough that NASA and ESA have both commissioned studies on how to detect and intercept such objects. The challenge is distinguishing an artificial object from a natural one, especially if the object is small and distant. 3i Atlas is closer. At Venus flyby, it was roughly 150 million kilometers from Earth, about the same distance as the Sun. That is close enough for Hubble to resolve the nucleus as more than a point, though not close enough to see details smaller than a few hundred kilometers. The James Webb Space Telescope, with its larger mirror and infrared sensitivity, might do better, but JWST observes in the infrared, not the radio. It could measure the comet's temperature, composition, and dust production, but it cannot detect 1420 MHz signals. For that, astronomers need radio telescopes, and they are using them. The Very Large Array in New Mexico, a collection of 27 radio dishes arranged in a Y shape across the desert, was retasked on November 3rd to observe 3i Atlas. The VLA can form a synthetic aperture tens of kilometers wide, achieving angular resolution fine enough to separate the nucleus from the coma and possibly from a trailing object. The Green Bank Telescope in West Virginia, the largest fully steerable radio dish in the world, has also been pointed at the comet. Green Bank is the flagship of SETI research in the United States, and its director, Dr. Karen O'Neill, confirmed in a brief email to colleagues that the telescope is now part of a coordinated multi-wavelength campaign. She did not elaborate. The Arecibo Observatory in Puerto Rico, which collapsed in 2020, is no longer available. Its loss is keenly felt. Arecibo could transmit as well as receive, and in 1974 it sent the famous Arecibo message toward the globular cluster M13, a symbolic greeting encoded in binary and transmitted at 2380 MHz. If Arecibo still existed, it could, in principle, attempt to communicate with whatever is transmitting from 3i Atlas. The VLA and Green Bank cannot transmit. They can only listen. So humanity is listening. Competing explanations are now crystallizing. One camp, led by traditional cometary scientists, insists the signal is a misinterpretation. Perhaps the 1420 MHz emission is real but natural, a maser, an amplified microwave emission caused by population inversion in excited molecules. Masers occur in space. Particularly in star-forming regions where water or hydroxyl molecules are pumped by infrared radiation into high-energy states and then release photons coherently. It is conceivable that conditions in the comet's coma, intense ultraviolet flux, collisional excitation, magnetic fields, could create a transient maser. The 37-second period might reflect the timescale of gas release, a breathing mode where pressure builds and releases cyclically. But masers are rare and require specific conditions. They also tend to be directional, beaming along paths defined by geometry and density gradients. For both Juice and ALMA to see the same maser implies the beam is very broad, or the observers are unusually lucky. And masers typically operate at specific molecular transitions: 22 GHz for water, 1665 MHz for hydroxyl, not 1420 MHz, which is the transition of neutral atomic hydrogen. Hydrogen masers do exist in laboratory settings, used as ultra-stable frequency standards in atomic clocks, but they require carefully controlled environments. A comet coma is anything but controlled. A second camp, smaller but growing, argues the signal is artificial but not alien. Perhaps 3I Atlas is not a comet at all, but a piece of human debris, a relic from a forgotten mission, or a secret military satellite that malfunctioned and was ejected onto an escape trajectory. The solar system is littered with junk: spent rocket stages, dead satellites, fragments from collisions. Most of it orbits Earth or the Sun in predictable loops, but occasionally something is perturbed by a close pass with the Moon or a gravitational assist from a planet and flung outward. If such an object left the inner solar system decades ago, traveling at a few kilometers per second, it could by now be far enough away that its origin is obscured. And if it carried a radio beacon powered by a long-lived radioisotope thermoelectric generator, it might still be transmitting. The objection to this scenario is orbital mechanics. To achieve a hyperbolic escape trajectory from the solar system, an object must be accelerated to more than 42 kilometers per second relative to the Sun, the solar escape velocity at Earth's distance. Human spacecraft reach such speeds by using gravity assists from planets, carefully timed flybys that steal momentum. Voyager 1, for example, Voyager flew past Jupiter and Saturn to achieve its current velocity of 17 kilometers per second relative to the Sun, still not fast enough to escape without help from the Sun's motion through the galaxy. 3I Atlas is moving at 34 kilometers per second relative to the Sun, faster than any human-made object. For it to be artificial and human-made, it would have to have been launched with a velocity we cannot achieve, or it would have to have received an enormous boost from an unknown source. Unless the Russians or the Chinese did something no one admitted. That is the kind of whisper circulating in intelligence circles, according to sources who spoke off the record. The third camp, the one that makes astrophysicists nervous and excites the public, is that the signal is both artificial and extraterrestrial. That 3I Atlas is, or carries, technology from another civilization, and that the 1420 MHz emission is deliberate, a greeting, a warning, a malfunction, or simply an operational signature, the electromagnetic hum of machinery never designed to be stealthy. Avi Loeb is the most visible proponent of this possibility, though he is careful to phrase it as a hypothesis requiring evidence. In his 2021 book Extraterrestrial, he argued that Oumuamua's anomalous acceleration could be explained if the object were a light sail, a thin sheet propelled by radiation pressure, and that such technology is not beyond the capabilities of advanced civilizations. He further proposed that interstellar space might be filled with debris from such civilizations: defunct probes, discarded components, wreckage from ancient conflicts, and that a small fraction of that debris could, statistically, pass through our solar system. The odds are low, but not zero. And as observational surveys improve, detecting smaller and fainter objects at greater distances, the discovery rate of interstellar visitors should increase. Loeb founded the Galileo Project in 2021, an initiative to search for technological signatures of extraterrestrial civilizations, including anomalous objects in space and unidentified aerial phenomena in Earth's atmosphere. The project operates independently of traditional SETI, which focuses on radio signals from distant stars. Loeb's strategy is to look nearby, on the assumption that if intelligent life exists elsewhere, its artifacts might be closer than the civilizations that built them. A probe launched 1 million years ago could still be functional, a light sail jettisoned during deceleration could still be drifting. And if such objects enter the solar system, we might notice them, if we are paying attention. 3I Atlas is now the target of that attention. But Loeb's hypothesis has critics. Many astronomers point out that invoking aliens is premature when natural explanations have not been exhausted. The history of science is littered with examples of phenomena initially labeled mysterious or supernatural that later proved mundane. Pulsars, when first discovered in 1967, were jokingly called LGM-1, little green men, because their regular radio pulses seemed too precise to be natural. Within months, astronomers realized they were rotating neutron stars. Fast radio bursts, detected starting in 2007, sparked speculation about alien megastructures. Now they are understood as emissions from magnetars, or colliding neutron stars. The lesson is clear. Extraordinary claims require extraordinary evidence, and a single anomalous signal, however intriguing, does not meet that standard. Yet the pushback against Loeb also reveals a cultural bias. Astronomy has long been cautious about speculating on extraterrestrial intelligence, wary of being dismissed as fringe or unserious. SETI researchers in particular have fought for legitimacy, emphasizing rigorous methodology and skepticism. The result is a field that, while open to the possibility of finding alien signals, is deeply conservative in interpretation. A signal must be verified, repeated, and analyzed exhaustively before conclusions are drawn. That conservatism is scientifically sound, but it can also delay recognition of genuinely anomalous data. 3I Atlas is forcing that tension into the open. Now consider the timing. The comet reached perihelion on October 30th, its closest approach to the Sun, and its brightness surged unexpectedly. 4 days later, on November 3rd, it flew past Venus. And the Juice probe detected the 1420 MHz signal. If the signal is related to solar heating, if the increased radiation flux activated something, then the perihelion surge and the signal are causally connected. That connection might be purely natural, heat vaporizing ice, releasing gas, creating conditions for unusual plasma behavior, or it might be artificial, heat reactivating dormant electronics, rebooting a transmitter that has been cold and silent for millennia. If the latter, then 3I Atlas is not merely a visitor, it is a messenger, and we have approximately 2.5 months to interrogate it before it becomes unreachable. On December 19, 2025, the comet will pass Earth at a distance of 270 million kilometers, about 1.8 AU, a safe margin that poses no threat but offers another observational window. By then, the solar glare will have diminished, and ground-based telescopes will have a clearer view. JWST will observe in infrared, mapping the comet's temperature and dust distribution. Hubble will image in ultraviolet and optical, looking for jets and fragments. The VLA and Green Bank will continue radio observations, tracking the 1420 MHz signal, if it persists, and searching for additional frequencies or modulation patterns. In March 2026, the comet will approach Jupiter, passing within 5 AU of the giant planet. Jupiter's immense gravity will not capture the comet. The trajectory is too fast. But it will perturb the orbit slightly, bending the path and accelerating the departure. After that, 3I Atlas will climb out of the solar system, moving into the Kuiper Belt and then the Oort cloud. And within a decade, it will be too faint and too distant for even the most powerful telescopes to track. It will rejoin the interstellar medium, lost to observation, carrying whatever secrets it holds back into the void, unless we intercept it. The idea has already been floated in internal discussions at NASA and ESA. A fast flyby mission, similar to New Horizons' encounter with Pluto, could reach the comet if launched within the next few months. The trajectory would require a gravitational assist from Earth or Venus to match the comet's speed and inclination, and the spacecraft would need to be small and light to fit on an available rocket. It would not land. It would not sample. It would simply photograph the nucleus at close range, measure its composition with onboard spectrometers, and perhaps, if the engineers are bold, attempt to communicate with whatever is transmitting the signal. That last option is controversial. Transmitting a message to an unknown object, even one that appears to be transmitting itself, raises questions of protocol and risk. Who decides what to say? What language or encoding to use? And what if the object is not a benign probe, but something hostile, or simply indifferent to human existence? The history of contact between civilizations on Earth suggests caution. First contact has rarely been equitable, but others argue that the risk is minimal. If the object is artificial and extraterrestrial, it has already detected us, or at least detected the Sun, and chose to pass through the inner solar system. If it intended harm, it could have done so already. If it intended communication, we are obligated to respond. And if it is merely defunct, a relic drifting on inertia, then transmitting a signal changes nothing. Stephen Hawking, before his death, warned against active messaging to extraterrestrial civilizations, arguing that any species capable of interstellar travel would likely be far more advanced than humanity, and might view us as resources to be exploited or threats to be eliminated. But Hawking also acknowledged that passive listening, SETI's traditional approach, is safe only if we assume other civilizations are not already aware of us. Earth has been leaking radio signals into space since the invention of radar and television, a growing sphere of electromagnetic noise, now extending more than 100 light-years from the Sun. Any civilization within that sphere, equipped with sensitive enough receivers, could detect us. In that context, actively transmitting a focused signal to a nearby object changes the calculus only marginally. The Galileo project, backed by private funding, is reportedly exploring the feasibility of a rapid response mission. Details are scarce, but sources close to the project suggest a launch window in January 2020 using a small spacecraft carried by a SpaceX Falcon Heavy rocket. The mission would rely on off-the-shelf technology, cameras, spectrometers, a radio transceiver, and a high-gain antenna. Total cost? Under $500 million, a fraction of flagship missions like JWST or Perseverance. The spacecraft would fly past the comet in late 2026 or early 2027, depending on orbital mechanics, and transmit data back to Earth in real time. If funded and approved, it would be humanity's first deliberate attempt to intercept an interstellar object. But even without a dedicated mission, the data are accumulating. JWST observed 3I Atlas on November 4th, capturing infrared spectra of the coma. Preliminary results, leaked to the press before official publication, show strong absorption features consistent with water ice, carbon dioxide, and silicate dust, all expected in a comet. But there is also an anomaly in the 3-micron band, a narrow absorption line that does not match any known molecule in the spectral databases. It could be an instrumental artifact. It could be a complex organic compound, a hydrocarbon or nitrile synthesized in interstellar space, or it could be something new. The Hubble Space Telescope, observing in ultraviolet, captured images of the coma showing asymmetric structure, a bright central region surrounded by concentric shells, like ripples frozen in time. Such shells are sometimes seen in comets that have undergone fragmentation or outbursts, but the spacing is unusually regular, about 15,000 kilometers between peaks. If those shells represent discrete ejection events, then the events occurred at regular intervals, roughly every 3 hours, implying a periodic process. 3 hours is 10^800 seconds. Divide by 37 seconds the period of the radio signal, and the result is 292. Not a round number, but close enough to suggest a possible connection. If the 37-second modulation is tied to rotation, and the 3-hour shells are tied to an ejection cycle, then the comet might be rotating 292 times per ejection event. That ratio feels arbitrary unless there is a mechanism, a buildup of pressure perhaps, released when stress exceeds a threshold, or unless something is counting. Think about what that means if it is deliberate. If the signal and the ejections are coordinated, then the comet's activity is not random. It is structured, following a program or responding to commands. That does not prove intelligence, but it moves the hypothesis from implausible to testable. The Juice team, meanwhile, has released a second data packet, this one labeled Anomaly Z08. The 1420 MHz signal is still present, now observed continuously for over 12 hours, and the modulation pattern has not drifted. The 37-second period is stable to better than 0.01 seconds, a precision that rules out chaotic tumbling or transient plasma effects. Moreover, the signal strength is increasing. At 1412 UTC on November 3rd, the signal was faint, barely above the noise floor. By 02 or UTC on November 4th, it had grown by a factor of 3. Either the source is becoming more active, or it is rotating in such a way that the beam is sweeping toward the observers, or it is moving closer. But the comet is not moving closer. It passed Venus and is now receding, heading outward toward its December encounter with Earth. The distance between Juice and the comet is increasing, so the signal strength should be dropping, not rising. Unless the source is not on the comet, unless the source is separate, trailing behind, and that trailing object is now emerging from the comet's shadow, either literally, eclipsed by the nucleus, or figuratively, obscured by the coma's plasma and dust. As the comet moves and the geometry shifts, the trailing object becomes visible, and its signal reaches the observers with growing intensity. ALMA confirmed this on November 4th with a high-resolution observation. The Chilean array can resolve structures as small as 0.1 arcseconds, which at the comet's distance translates to about 7,000 kilometers. The images show two sources of 1420 MHz emission, one centered on the nucleus, weak and diffuse, and a second source offset by approximately 50,000 kilometers along the tail axis, compact and bright. The compact source is where the modulated signal originates. 50,000 kilometers. That is more than 3 times the diameter of Earth. It is far enough that the object is not part of the coma in the traditional sense. It is not gas or dust clinging to the nucleus by weak gravity. It is a separate entity coasting along the same trajectory, possibly ejected from the comet or possibly traveling in formation. Paul Chodas, breaking his silence, released a terse statement on November 4th. CNEOS is collaborating with ESA and international partners to analyze anomalous observations of 3I Atlas. We are treating this as a high-priority investigation. Further updates will be provided as data are verified. The statement says everything and nothing. High-priority investigation, anomalous observations, data verification. These are the phrases of institutional caution, the language of organizations that cannot afford to speculate publicly, but also cannot ignore the evidence. Elon Musk, predictably, is less restrained. His posts on X have become a running commentary, mixing technical details with provocative questions. If this is a probe, where did it launch from? Triangulum is 3 million light-years away. That's intergalactic. More likely a star in the solar neighborhood, maybe 10-20 light-years. Fast radio bursts travel billions of light-years. This is right here. Another post. Starshield has tracked over 140 modulation cycles. Zero drift. Zero jitter. This is a clock. A clock. That is what it sounds like. And clocks are built, not grown. The ESA Science Directorate convened a second teleconference on November 5th, this one including representatives from the International Astronautical Federation, the United Nations Office for Outer Space Affairs, and several national space agencies. The agenda, according to a leaked summary, covered three topics: observational strategy, public communication, and contingency planning. The third item is the most revealing. Contingency planning implies scenarios where the situation escalates, where the object behaves in ways that require coordinated response. That could mean anything from a course correction, bringing the object closer to Earth, to the object transmitting a message that demands a reply, to the object doing nothing at all and the signal simply stopping, leaving more questions than answers. What does humanity do if the object is intelligent and makes contact? The answer depends on what contact looks like. If the object transmits a clearly artificial message, a sequence of prime numbers, for example, or an image encoded in binary, then the message itself is evidence. It can be studied, decoded, and perhaps answered. If the object remains silent, broadcasting only the carrier wave, then interpretation is ambiguous. The signal might be a beacon, meant to attract attention without conveying specific information. Or it might be internal, a byproduct of machinery, not intended for communication, like the hum of a power line or the ping of a sonar. SETI protocols, developed over decades by organizations like the International Academy of Astronautics, provide a framework for such scenarios. The protocols emphasize verification first, confirm the signal is real, rule out natural and human-made sources, and replicate the observation with independent instruments. Then, if the signal passes those tests, inform the international community before taking further action. Finally, if response is warranted, a message should be crafted collectively, representing humanity as a whole rather than any single nation or institution. Those protocols assume the signal comes from light years away, from a distant star where response time is measured in decades or centuries. 3I Atlas is different. It is here, now, moving through the solar system at 34 kilometers per second, and it will be gone within months. There is no time for committees or consensus. Decisions must be made quickly, with incomplete information under pressure. That pressure is already visible. Online forums are ablaze with speculation. Reddit threads on RR Space and SETI are accumulating thousands of comments per hour. YouTube videos with titles like Alien Probe Confirmed and 3I Atlas First Contact are racking up millions of views, most of them breathless hype, but some featuring credible scientists attempting to explain the data responsibly. Twitter, or X as Musk has rebranded it, is a storm of arguments. Skeptics demanding rigor, enthusiasts declaring vindication, conspiracy theorists claiming governments are hiding the truth. The truth is simpler and more frustrating. Nobody knows yet. What we have is a signal, a tantalizing, repeating, highly structured signal, at a frequency humans chose for SETI because it is universal. And that signal is coming from an object that originated outside the solar system and is passing through the inner planets at high speed. It is accompanied by visual anomalies, brightness surges, concentric shells, a trailing compact source that do not fit comfortably into existing models of cometary behavior, but are not, individually, impossible. If the signal is natural, then 3I Atlas is teaching us something new about physics or chemistry. Perhaps interstellar comets, forged in environments different from our own Kuiper Belt or Oort cloud, behave in ways we have not anticipated. Perhaps the extreme cold of interstellar space, sustained for millions of years, creates exotic ice phases or metastable molecules that react violently when heated. Perhaps magnetic fields, twisted and amplified by interaction with the solar wind, generate coherent emission in ways not yet described by theory. Any of these would be discoveries worthy of publication, analysis, and possibly prizes. If the signal is artificial but human, then 3I Atlas is a reminder of our own technological legacy and the difficulty of tracking objects once they leave the immediate vicinity of Earth. Lost spacecraft, debris from secret programs, wreckage from collisions, all of it continues to orbit, and some of it eventually leaves. The solar system is vast. Our catalogs are incomplete. Something launched decades ago and forgotten could, plausibly, reappear in an unexpected place. And if the signal is artificial and extraterrestrial, then 3I Atlas is the most important object humanity has ever observed. It is physical evidence that we are not alone, that intelligence exists elsewhere, and that the galaxy contains travelers, explorers, refugees, machines, something that cross the voids between stars. It means the Fermi paradox, the question of why we have not yet seen clear signs of alien civilizations despite the apparent likelihood of their existence, has an answer. We have seen them. We just didn't recognize them until now. Each possibility carries profound implications. The natural explanation would revolutionize cometary science and planetary formation theory. The human explanation would expose gaps in our tracking networks and perhaps embarrassing lapses in institutional memory. The extraterrestrial explanation would transform not only science, but philosophy, religion, culture, and geopolitics. It would force humanity to reconsider its place in the universe and to confront the possibility that others are watching, have been watching, and might judge us by how we respond. So what comes next? Observationally, the campaign is intensifying. JWST will observe the comet again on November 10th, targeting the trailing compact source with its near-infrared spectrograph to measure temperature and composition. If the object is a clump of ice and dust, it will radiate in the infrared at temperatures determined by solar heating, probably around 200 to 300 Kelvin. If the object is metallic or composed of materials not found in natural comets, its thermal signature will differ. JWST's sensitivity is high enough to detect temperature variations of a few degrees, and its spectrograph can identify molecular absorption lines with exquisite precision. Hubble will image the comet in optical wavelengths on November 12th, constructing a time-lapse sequence to track the movement of the trailing object relative to the nucleus. If the two are gravitationally bound, the trailing object should follow an elliptical orbit around the nucleus, appearing to swing back and forth over hours or days. If the two are merely traveling parallel trajectories, the separation should remain constant or change predictably due to differential solar radiation pressure. Any deviation, acceleration, deceleration, course correction would indicate active maneuvering. The VLA in Green Bank will monitor the 1420 MHz signal continuously for at least another 2 weeks, recording the full waveform and searching for fine structure. If the modulation encodes information, it might be detectable as variations in amplitude, frequency, or phase beyond the simple 37-second periodicity. Cryptanalysts and information theorists are already volunteering to analyze the data, though ESA and NASA have not yet decided whether to release the raw signal to the public. Doing so would invite independent verification and crowdsourced analysis, accelerating discovery. But it would also invite noise, false patterns, premature conclusions, and speculation that could mislead or alarm. The International Asteroid Warning Network is coordinating radar observations using the Goldstone and Arecibo successor facilities. Radar can measure the size and shape of the nucleus with meter-scale resolution, determine the rotation state, and detect any large fragments or companion objects. It can also, potentially, illuminate the trailing compact source and measure how it reflects or absorbs radio waves. Metals reflect strongly. Ice absorbs weakly. The distinction would be diagnostic. China's Tianwen-3 mission, currently en route to Mars, has been retasked to observe 3I Atlas during a brief window in mid-November when the geometry allows. Tianwen-3 carries a high-resolution camera and a spectrometer, and though the spacecraft is not designed for comet observation, its instruments are capable. The Chinese National Space Administration has not commented publicly, but sources within the agency confirm the retargeting. If Tianwen-3 captures useful data, it will mark China's first significant contribution to the study of an interstellar object, And then there is the possibility of direct communication, breakthrough. Listen, the SETI initiative funded by Yuri Milner has proposed transmitting a message toward the trailing compact source at 1420 MHz, the same frequency the object is using. The message would be simple: a series of pulses encoding the integers 1 through 10 in binary, a universally recognizable pattern that demonstrates mathematical understanding. If the object is capable of receiving and interpreting, it might respond. If it is merely a transmitter, or if it is defunct, the message will go unanswered, costing nothing but a few hours of telescope time. The proposal is controversial. The United Nations Outer Space Treaty, ratified by 111 countries, does not explicitly prohibit active messaging to extraterrestrial objects, but it does require that space activities be conducted for the benefit of all nations and with due regard to the interests of others. Sending a message without international consensus could be seen as overstepping, a unilateral action with collective consequences. But Breakthrough Listen is privately funded, not bound by governmental restrictions, and the transmission could be executed from any radio telescope willing to participate. Loeb supports the attempt. "If we don't try, we'll never know," he said, in a video posted on November 5th. "The object is here now within reach. In a few months it will be gone forever. This is not a distant star we can observe at leisure. This is a once-in-a-lifetime opportunity, and caution should not paralyze us into inaction." Others disagree. Dr. Jill Tarter, former director of the SETI Institute and a veteran of decades of radio searches, urged restraint in a public statement. "We have no idea what we're dealing with. Transmitting a message could be harmless. It could also provoke a response we are not prepared for. The prudent course is to observe, analyze, and build consensus before acting." The debate is unfolding in real time, in scientific journals and social media, in government meetings and private conversations. There is no clear consensus, no mechanism to enforce a decision, and no time to deliberate indefinitely. Meanwhile, the comet continues its journey, indifferent to the turmoil it has caused. Read between the lines of every official statement, and you will find the same subtext: uncertainty. Uncertainty about what the object is. Uncertainty about what the signal means. Uncertainty about what humanity should do. But beneath that uncertainty lies a deeper question, one that has haunted astronomers since the first telescopes turned skyward. Are we alone? For centuries, that question was philosophical, a matter of belief rather than evidence. The universe is vast, billions of galaxies, each containing billions of stars, many of those stars orbited by planets, and the sheer scale suggested that life, even intelligent life, should be common. But the Fermi paradox pointed to the silence. If civilizations exist, where are they? Why haven't we heard from them? Possible answers range from the hopeful to the grim. Perhaps civilizations are common but short-lived, extinguishing themselves through war, pollution, or resource depletion before they achieve interstellar travel. Perhaps the galaxy is teeming with life, but intelligent life is rare, or communication is difficult, or we are simply looking in the wrong places at the wrong times. Perhaps we are the first, the elder species, alone not because others do not exist, but because they have not yet arisen. Or perhaps we are being watched, studied, and deliberately avoided, like animals in a zoo. 3i Atlas has not answered the Fermi paradox, but it has transformed the question from abstract to immediate. If the object is artificial, then someone, somewhere built it. And if they built one, they likely built many. The galaxy might be crisscrossed with probes, drifting on Newtonian trajectories, visiting stars at random, reporting back to civilizations that might still exist, or might have vanished eons ago. Earth has been visited by 2 confirmed interstellar objects in 8 years. How many more have passed unnoticed, too small or too dark to detect? How many more will we find as surveys improve? Stop and consider that. If interstellar probes are common, then first contact is not a singular event waiting to happen. It is an ongoing process, a gradual accumulation of evidence from multiple sources. Oumuamua was the first hint. Borisov was a control, a natural object proving that not every visitor is exotic. 3-eye Atlas might be the confirmation, and future objects, 4-eye, 5-eye, 6-eye, will refine the picture, building a statistical sample large enough to draw conclusions. That is the optimistic scenario. The pessimistic scenario is that 3-eye Atlas is another false alarm, another ambiguous signal that dissolves under scrutiny, leaving us exactly where we started, alone, uncertain, and staring into the void. Which brings us back to the data. The 1420 MHz signal has now been observed for over 60 hours. The 37-second period is stable. The modulation envelope is reproducible. The trailing compact source is confirmed by multiple independent instruments. These are facts, not speculation, and they demand explanation. Natural hypotheses are struggling. A masser requires population inversion, and no plausible mechanism has been identified that could sustain 1420 MHz masser emission for hours in a comet coma. A plasma instability could oscillate, but 37 seconds is far too slow for typical instabilities, which operate on millisecond to second time scales. Rotation is possible, but it requires the nucleus to have a highly asymmetric emission pattern, stable over many rotations, and no such pattern has been observed in optical or infrared imaging. Artificial hypotheses fit the data better, but raise uncomfortable questions. If the object is human-made, why is there no record of its launch? If it is extraterrestrial, why is it here, now? And why is it transmitting at a frequency we chose for SETI? The coincidence is striking. 1420 MHz is not arbitrary from a physics perspective. It is the spin-flip transition of hydrogen, a fundamental property of the universe. But it is also not the most efficient frequency for communication. Higher frequencies allow faster data rates. Lower frequencies penetrate obstacles better. The water hole, the band between the hydrogen line at 1420 MHz and the hydroxyl line at 1665 MHz, is quiet and protected, but it is not unique. Unless the frequency choice is deliberate. Unless whoever built the transmitter knew that intelligent species capable of radio astronomy would recognize 1420 MHz as significant, unless the signal is designed to be noticed. That reasoning leads to an unsettling conclusion. If the signal is a beacon, it worked. Humanity noticed. And now we face the next question. What do we do? Answering that question requires understanding intent, and intent is ambiguous. A beacon could be an invitation. It could be a warning. It could be a territorial marker, a claim staked in the electromagnetic spectrum. Or it could be neutral, a navigational aid or a distress signal, devoid of emotion or agenda, simply a machine doing what machines do. The trailing compact source, if it is a discrete object, is too small to image directly with current telescopes. At 50,000 kilometers from the nucleus, subtending an angle of roughly 0.03 arcseconds at Earth's distance, it is below the resolution limit of even JWST and Hubble. Radar might provide shape information, but radar observations require precise timing and favorable geometry. The object is receding, moving outward from the sun, and soon it will be too far for radar to reach, which means the window for detailed study is closing. December 19th, when the comet passes Earth, is the last opportunity for comprehensive observation from Earth-based and near-Earth space-based platforms. After that, the comet will be beyond the orbit of Mars, fading rapidly as solar illumination decreases and distance grows. By mid-2026, it will be fainter than magnitude 25, detectable only by the largest telescopes with long exposures, and spectroscopy will be impossible. By 2027, it will be effectively gone, a moving point of light lost among the stars, and any signal it emits will be too weak to detect across the growing distance. That is why the Galileo project's proposed intercept mission is urgent. If launched in January 2026, the spacecraft could reach the comet by late 2026 when the comet is near Jupiter. The flyby would be brief, minutes or seconds, depending on relative velocity, but instruments could capture close-range images, measure the magnetic field, sample the coma with a mass spectrometer, and attempt to detect the 1420 MHz signal at close range, possibly triangulating its source. The mission profile is aggressive, relying on a gravitational assist from Earth or Venus to match the comet's trajectory and a high-speed encounter that leaves no room for error. The spacecraft would pass within a few hundred kilometers of the nucleus, close enough to resolve surface features if the nucleus is solid or to plunge through the coma if it is diffuse. Collision risk is non-negligible, especially if the comet is shedding debris, but the scientific return justifies the risk. Funding is the bottleneck. NASA's budget for unplanned missions is limited, and ESA is similarly constrained. The Galileo project has private donors, but $500 million is not trivial. Negotiations are ongoing, and sources indicate that several technology billionaires, names not yet public, are considering underwriting the mission in exchange for naming rights and early access to data. That is not how science is traditionally funded, but these are not traditional circumstances. And there is a philosophical dimension. If the object is artificial, does humanity have a moral obligation to study it? To attempt communication? To leave it alone? The question parallels debates over contact with uncontacted human tribes. Some argue for non-interference, allowing the other to remain isolated by choice, while others argue that contact is inevitable and should be managed responsibly. But 3I Atlas is not isolated by choice. It is moving through our solar system, broadcasting a signal, and it will leave whether we engage or not. The choice is not whether to interfere, but whether to take the opportunity we have been given. Think about what that means for future generations. If we act, and if the object is artificial, humanity will be remembered as the species that made first contact. Schools will teach the moment. Historians will analyze the decisions. Philosophers will debate the implications. And if we fail to act, if we let the object pass unexamined out of caution or indecision, future generations will ask why we hesitated when the universe offered an answer to its oldest question. The pressure is immense. Scientists are trained to avoid premature conclusions, to demand replication and rigor. But science is also driven by curiosity, by the willingness to explore the unknown and accept uncertainty. 3I Atlas embodies that tension. It is data and mystery, evidence and enigma, close enough to study, but moving too fast to be complacent. November 6, 2025. The signal continues. The modulation has not changed. The trailing compact source remains distinct, offset from the nucleus, stable in position and brightness. New observations from the Hubble Space Telescope show faint streamers connecting the compact source to the nucleus, visible only in ultraviolet, suggesting a tenuous flow of material or perhaps a magnetic field line made visible by fluorescence. The streamers are filamentary, reminiscent of solar coronal loops, or the magnetic structures seen in planetary magnetospheres. If those streamers are magnetic, they imply a field strength on the order of microteslas, far stronger than expected for a comet nucleus. Natural bodies generate magnetic fields through dynamos, electrically conducting fluids in motion, like Earth's molten core or Jupiter's metallic hydrogen layer. Comets are too small and cold for dynamos, unless the object is not a comet. Unless it contains conductive materials arranged in configurations that generate or trap magnetic fields, either passively like a permanent magnet or actively like an electromagnet. The JWST spectrum from November 10th will test this. If the trailing object is metallic, its infrared emission will be distinct, showing reflected sunlight rather than thermal glow, and its temperature will be lower than surrounding dust. If it is icy, The temperature will match solar heating models, and absorption features from water or carbon dioxide will appear. If it is something else, ceramic, composite, exotic matter, the spectrum will not match any known material. We will know in 4 days. 4 days is an eternity in modern news cycles, but a blink in the timeline of astronomy. The universe operates on scales of millions and billions of years. Stars form and die. Galaxies collide and merge. Civilizations rise and fall, if they exist at all, and their signals propagate at the speed of light, taking centuries or millennia to cross interstellar distances. Against that backdrop, 3I Atlas is instantaneous, a flash of presence in the solar system that will be over before most people realize it began. But those 4 days feel like waiting for a verdict. Scientists are restless. Data is being analyzed and reanalyzed. Models are being refined. Hypotheses are being tested against observations, and weaknesses are being exposed. The natural explanations are not holding up well. The artificial explanations remain speculative. And the only certainty is that more data will arrive, and with it, more clarity or more confusion. Online, the mood is shifting from excitement to impatience. Where is the official statement? Why haven't governments disclosed more? Conspiracy theories are proliferating, that NASA and ESA know the object is artificial, but are suppressing the information to avoid panic. That the signal is a hoax, fabricated by hackers or rogue scientists seeking attention. That the object is not a comet, but a weapon, and the militaries of the world are preparing for conflict. None of these theories have evidence, but they reflect the anxiety of a species confronted with ambiguity on a cosmic scale. Responsible scientists are pushing back, emphasizing the need for patience and rigor. But patience is difficult when the object is receding, when the window for observation is narrowing, when every day might bring the last clear data before the signal fades below detectability. So we wait. We wait for JWST. We wait for Hubble. We wait for radio telescopes to accumulate hours of signal, building statistics, searching for patterns within the 37-second cycle. We wait for radar to probe the nucleus and the trailing object, measuring size and shape and reflectivity. We wait for funding decisions on the intercept mission. We wait for a breakthrough, a piece of evidence so compelling that it forces conclusion. And while we wait, the comet moves. 34 kilometers every second, 2,000 kilometers every minute, 120,000 kilometers every hour. A distance equal to a third of the way to the moon every hour, pulling it farther from the sun and deeper into the outer solar system. If the object is artificial, it is patient. It does not hurry. It does not deviate. It broadcasts its signal, steady and unchanging, as though time is irrelevant, as though it has been waiting far longer than humanity has existed and will continue waiting long after we are gone. Or perhaps it is not waiting. Perhaps it is simply passing through, indifferent to the inhabitants of this small yellow star, executing a program written eons ago by creators who may no longer exist. Either way, it is here. It is real. And it forces a question that cannot be avoided. If the data are correct, if the signal is artificial, if the source is a discrete object traveling with an interstellar comet, if the modulation is too precise to be natural, how deep does this mystery go? Is 3I Atlas unique, or is it one of many? Are we being visited deliberately, or is this encounter random, a statistical accident in a galaxy filled with wanderers? And if civilizations send probes into the void, launching them in all directions to explore and report, where are the others? How many have passed through the solar system unnoticed? How many are still out there, drifting between stars, waiting for a sun to illuminate them and observers to ask the right questions? The answers, if they exist, are not yet within reach. But for the first time in human history, they feel close.